Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review the topic of logs. So this is the definition of a log. If a to the power of x equals b, then x equals log a of b. Logs are just ways to take what's in the power and make it the subject of an equation. So when we have log ab, we're saying what power do you raise this base to get b? So for log 4 of 64, we're saying, what do you raise 4 to get 64? And that's 3, because 4 to the power of 3 is equal to 64. For log 2 of 10, we're saying, what power do you raise 2 to get 10? Now, 10 is not a power of 2, so the answer to this is irrational. On the graphics calculator, you can put log 2 of 10 straight in. On the scientific calculators, because you can't input the base, you need to write it like this. And it's about 3.32. And that's because 2 to the power of about 3.32 equals 10. Now, when you just see a log by itself with no base, you assume it's base 10. So, log base 10 over 10th is saying, what do you raise 10 to get 1 over 10? And that's, of course, minus 1. 10 to the power of minus 1 is 1 over 10. When you see ln, it always means log base e. So this is saying, what do you raise e to get e to the power of 7? Well, of course, that's 7. E to the power of 7 gives you e to the power of 7, this thing there. So this one here, the base is just a. We're saying what power do you raise a to get 1 on root a? We need to write this as a power of a. So it's a to the power of a half because of the square root, and because it's on the bottom, it's a to the negative a half. If you raise a to the power of negative a half, you get 1 on root a. So these last two, it turns out, are undefined. You can't raise 2 to any power to get 0. That's why that's undefined. And similarly, you can't raise 3 to any power to get minus 1. If you raise a positive number to any power, the answer's always positive. So logs are really useful at solving exponential equations where the thing you want to find is part of the power. So let's look at this question here. So this is an exponential equation because the unknown's part of the power. We're going to undo what's been done to x in the opposite order to BIDMAS. So what we're going to do first is we're going to subtract 2 from both sides, and then we're going to divide each side by 3. So now you've got 4 to the power of something equals 8. Logs would be very useful here. So we need to find out what the power is. So x minus 1 would be log base 4 of 8. Now, log base 4 of 8 is equal to 1.5 because 4 to the power of 1.5 equals 8. So the power that goes here must be 1.5. X minus 1 equals 1.5, and so x is equal to 2.5. All right, let's have a quick look now at log laws. So there's 3 sort of laws here plus the change of base formula. The first law says when you add logs of the same base, you just multiply their powers. That's what we've done here. So log 3 of 8 plus log 3 of 6. What you would do when you're adding logs is you keep the same base and then you just multiply the 2 powers. So 8 times 6 is 48. So the next log law says when you subtract logs of the same base, you divide their powers. So if I have 2 logs here of the same base that are being subtracted, you always keep the same base and you divide the power. So 12 divided by 3 is 4. So for this one here, this says if you have a second power, you can simply move it to the front. So how would I simplify log a of 9? Well, 9 is equal to 3 squared. So I can write it like this, and then I can move the second power to the front. This will be 2 log a of 3. Note that these 3 laws are like the opposite of index laws. So remember when you multiplied the bases, you added the powers. For logs, it's the opposite. When you add the logs, you multiply the powers. And this one's analogous to the division law for indices, and this is the power to a power law. So number 4 here is the change of base. This is if you have logs in one base, like C, and you want to change it to another base of A. So that's really handy, it turns out, when we come to do calculus, because differentiating log base E is easy. I can easily write this as an expression with log base E's. So new base and power on top, and new base and old base on the bottom. All right, let's see how we can use this to solve logarithmic equations. So we looked before at exponential equations. Now we look at a logarithmic equation where the thing we want to find is part log. So we're going to use the log laws to combine this into one log because we're subtracting. So what we do is we keep the same base and we divide the powers. So it's going to be x plus 12 over x minus 12. Now, to make this solvable, we also want to change this into log base 2. Then we can cancel the logs. So if I want to write 2 as log base 2 of something, what number goes in the box? Well, it's actually just 2 to the power of 2, which is 4. So I can write 2 as log base 2 of 4. This is equal to 2 because 2 to the power of 2 equals 4. So now that I've got log base 2 on both sides, I can cancel those logs, and I'm just left with x plus 12 over x minus 12 is equal to 4. So what I'm going to do now is multiply each side by x minus 12. I'm going to expand the brackets, and then when you have a linear equation like this and the pronumerals on both sides, you subtract the coefficient with the lowest pronumeral. So I end up with 12 equals 3x minus 48. Add 48 to both sides, divide by 3, and you get x equals 20, and we're done. All right, let's now have a quick look at graphing logarithmic functions. So we're looking at graphing equations of this form, and they always have these features. So they always have a vertical asymptote at x equals the negative of whatever's in the brackets. The reason is you can't have log base a of 0 because no positive power can be raised to something to get 0. They always pass through this point. Just adding this extra point might help you see the direction of the curve. Now, if the base A is greater than 1, it goes like this, increasing at a decreasing rate. And if the base here is less than 1, like it's a fraction, then it goes like this. It decreases at a decreasing rate. So for any log graph, the domain is always x has to be greater than the negative of this because, as I said, you can't have log base A of 0, but y can take any value. All right, let's look at graphing this function here. So I want you to be aware that log base 1/3 of x, we can change the base so it's log base 3. So it'd be log base 3 of power over log base 3 of 1/3. Now, log base 3 of 1/3 is equal to minus 1 because 3 to the power of minus 1 equals 1/3. So what I'm saying is this is actually the same as the graph of minus log 3 of x plus 3 minus 1. These two are exactly the same graph. Now, because the base here, 1/3, is less than 1, it's going to look like this. It's going to start off big and decrease at a decreasing rate. So when we're graphing, the first thing we should do is graph the asymptote at x equals minus b. So minus b here is minus 3. It's going to have a vertical asymptote here. It's never going to hit this asymptote or go past it. Once again, the reason for the asymptote, you can't raise 1/3 to any power to get an answer of 0. So here the value of c is minus 1. So we can go 1 to the right of the asymptote and go down to c. So 1 to the right of the asymptote and down to c, it goes through this point minus 2, minus 1. So to find the y-intercept, we do what we've always done and let x equal 0. So the y-intercept here would be log base 1/3 of 3 minus 1. You can put that straight on your calculator, you get minus 2. So the y-intercept is down here at minus 2. To get the x-intercept, we let y equal 0. So then we solve this equation here. So we add 1 to both sides. And the way we get rid of the log here is raising 1/3 to both sides. So 1/3 to the power of 1 is just 1/3. And if you raise this side here to the power of 1/3, the log goes away, you're just left with x plus 3. So then we simply subtract 3 from both sides, we get x is minus 8 over 3. That is the x-intercept. And x is minus 8 over 3 is about there. Now, because we know the graph is going to follow this shape, we have enough information to graph. It just goes through all of these points. It gets closer and closer to, but never hits the asymptote. Note that this will just keep going and going forever. Y value will keep going down. It just goes down very slowly. All right, let's now look at some calculus. So when differentiating, you need this rule, and integrating, you need this rule. So to differentiate log of a function, you put the function on the bottom and its derivative on the top. Note that this derivative has no logs in it. So if I want to differentiate y equals ln x, it's just going to be 1 over x. X on the bottom, its derivative on the top. If I want to differentiate this function here, same thing. What I do is I put the function, what's in the brackets, on the bottom, so x squared plus x, and I put its derivative on top. The derivative of x squared plus x is 2x plus 1, and then I'm done. So how would I differentiate log x? Remember, if no base is written, we assume it's 10. Well, I can actually use the change of base formula here. I can write this as log base e. Why? Because I know how to differentiate e. So this number on the bottom, ln 10, is just a constant. The derivative of ln x is 1 on x. So the derivative here will just be 1 on x ln 10, and we're done. So similarly, we can use logs to help us differentiate something like fx equals 2 to the power of x. You see, 2 to the power of x can be written like this. So e to the power of natural log of 2 to the power of x is 2 to the power of x. But remember the log law, I can move this x to the front. So the way I differentiate e to the power of something, remember what I do is multiply by the derivative. So the derivative of the power, derivative of x ln 2 is just ln 2, and then I leave the e and the power alone. But remember, e to the x ln 2 is just, this thing here is 2 to the power of x. So the derivative of 2 to the power of x is ln 2 times 2 to the power of x. Derivative of 4 to the x would be ln 4 times 4 to the power of x, and so on. So let's now look at integration. So this is just the opposite of this. If you integrate where you have the function on the bottom and derivative on the top, the integral is just ln of that function on the bottom, and you need to remember to add the c. So the integral of 1 on x is just ln of x plus c. So let's say I want to integrate this here. Well, I have a function on the bottom, and I have something close to the derivative on top. See, the derivative of this function is 2x. So what I really want is a 2x on top. But I can't just multiply by 2 there. If I put a 2 there, I have to divide by 2 or multiply by a half. See, multiplying by 2 and multiplying by a half, I haven't changed this function. I've just written it in a different way. I've written it in this form. So now the integral will just be a half, and the integral of function on the bottom and its derivative on top is just the natural log of that function, and we have to remember to add the c. So the easiest way to integrate this function would be to divide. So I'm going to divide everything by x to the power of 4. So x cubed over x to the power of 4 is x to the power of minus 1, or 1 on x, and 4x over x to the power of 4 is just 4 over x cubed. So to integrate 1 on x, we just get natural log of x. The integral of 4 over x to the power of 3, we did that last semester, it's 4x to the power of minus 3. So you increase the power by 1 and divide by the new power, and we get this. So just to make it a little easier to work with, we could write it as ln x minus 2 on x squared plus c. If you were to differentiate this function, you would get that. All right, let's now look at some logarithmic modeling. So logarithmic modeling is when we use logs to solve real-world problems. So an example of where logs are used in the real world is sound. This formula here tells you D, the number of decibels of a sound, and that's how we measure how strong a sound is. So I is the intensity of the sound that we're talking about. It's measured by its energy output, and I0 is the intensity of the softest sound that can be heard by the average human here. I0 is a constant. It's just a measure of energy in watts. I think it's like 10 to the minus 12 watts or something like that. So let's answer this question here. One sound is 200 times more intense than the other. What will be the difference in decibels between the two sounds? So here I'm going to have sound 1 is going to have decibels 1, whatever that is, with intensity 1. And I'm going to have a second sound. I'm going to call D2 its number of decibels and I2 its intensity. So logarithmic scales like these are all about proportion. The number of decibels a sound has is determined by how many times more intense it is than I0, this softest sound that can be heard by the human ear. So in this case, we're told that I1 over I2 is equal to 200. That's what it means, that the intensity of the first sound is 200 times the intensity of the other sound. So what we want to know is the difference in decibels. How many more decibels is the louder sound than the softer sound? Is it 30 decibels more or 20 decibels more or whatever? So D1 minus D2 is going to be, this is D1, so it's going to be the same formula, but I use I1, and then I'm going to subtract D2. So now what I can do is take out a common factor of 10, and I can use my log laws here to combine this into one log. Remember, what we do is we divide the powers. Now, this fraction divided by this fraction, we'll see the I0s cancel out, and I'll be left with log base 10 of I1 divided by I2. But I was told in the question, I1 over I2 is 200. So this is equal to 10 log 10 of 200, and you can put that straight in your calculator. And the answer we get is about 23. So if one sound is 200 times as intense as another, it will be 23 decibels more. So for example, a sound that's 100 decibels is 200 times more intense than a sound that's 77 decibels. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.